Recording is rolling. It is Thursday, May 2nd. We're going to finish this quantum mechanics journal today. So you guys got journals out. Yeah, by the end of class, if you have all these quadrants finished, then you can turn this to the gray tray. You'll be good to go. Of course, we're on this fun schedule today. So just for context, all right, we're ready for laser. Okay, you guys ready to do laser? It's laser time. Lasers, how do they work? There you go, lasers. All right, so got his laser diagram drawn. All right, let's say I got a mirror here, mirror. All right, and the other side is also a mirror, say with a hole cut in it. All right, we're just gonna let the photons bounce back and forth. Right? All right, now in classical mechanics, you say, well, that just seems like it'd be random, then, right? So what's the difference here, right? So in what is a laser? Like, how is laser light different from, say, like incandescent light or fluorescent light? Guys, here, you got your quantum, guys, right? So incandescent light can have light at all different wavelengths, it's all different colors, and they won't be in phase necessarily, anything like that, right? But a laser light does. They're all same wavelength. Right? That's why you get, say, one color. It could be like a red laser or a green laser, right? And they all have the same polarization. Right? Now, why would that be? Because this is a quantum effect. Because photons, well, what is a photon? Is it a particle? Well, yeah, kind of, but it's also a wave. So what about like a bunch of photons? Well, now it's ambiguous. Is what you have. So they're from a quantum view, statistically more likely to have the same polarization, be in phase and have the same polarization. Let's see, because in quantum mechanics, particles are not readily distinguishable. Right? So what is one particle, another particle, right? That's I kind of draw this here. I'm gonna draw a bunch of waves all being in phase, right? And the same wavelength, the same phase. All right, boom, there you go. Laser light, laser light. All right, everybody got laser. Switch over to Hawking radiation. Ooh, we're about to take a trip right near a black hole. Ooh, all right. My screen froze again. All right, that's right. I said most of the stuff there. So, all right. So, yeah, here's a little bit more stuff. Sorry, my screen froze, but that's all right. Got most of it here. Right, so, what is out in deep space? Like, you go like to beyond our solar system, between solar systems and the galaxies. That's pretty right. I think I remember reading that something like 1 hydrogen per cubic meter or something kind of like that. Right? But so almost probably as close to a vacuum as you can get. Right? Right? But in quantum mechanics, there's this interesting effect that from an actual vacuum, from nothing, you get these particle-antiparticle pairs just popping up, right? But just immediately annihilate each other, right? So it doesn't really violate conservation of energy or anything like that, right? But near the edge of a black hole, you can have the scenario where the antiparticle, right, that has negative mass, right, will fall into the black hole. Right? But the particle, say with positive mass and energy, right, can have enough energy to escape. And the consequence of that, right, if you have, say, like these positive mass particles escaping into the universe. Right? For example, this might be like an electron, and this might be a positron. Right? The electron could possibly have enough energy to escape into the world. That is your Hawking radiation. Hawking radiation. Okay. Okay. And but then the antiparticle, which has negative mass, is going to fall into the black hole. And that will eventually dissipate the black hole. So black hole will eventually dissipate. Okay. Now, this takes a crazy long time, and it depends actually on the size of the black hole too. Okay? Now, this universe has only been around for about 14 billion years, give or take. You can imagine a huge mass like a black hole being slowly dissipated by this process. That would probably take like at least 1 trillion years or something crazy. So we're talking about like real deep time for this to happen. So is a black hole like the end of everything and stuff gets sucked into it and it's just stagnant forever? Well, no, not quite. Right. So it's like slowly eaten away by this process. Right, so you guys got Hawking radiation. All right. Flip over here. All right. There's an article I dug up. Let's see, do I have it? No, not that one. Find this. Some years back, right? That kind of reminded me of that same idea. Right? Let's zoom in here. Scientists create light from a vacuum. If you read those details, what they did is they took a mirror and they vibrated it at a relativistic speed. And then that process of particles and antiparticles popping up, it was able to separate those up. Right, so next one, radioactive decay. Radioactive decay. Ooh, that's a Geiger counter. Radioactivity. You guys see that last detail? Rocks have been found 4.5 billion years old. That's where, if you say, look up in a textbook or on the internet, what is the age of the Earth? That's the number they'll give you, 4.5 billion years. And this is exactly how they know this. Right. So here's a chain for a decay series for radioactive elements, right? Until you get down to lead, right? So if you start in the top uranium, now there is one above this, which is plutonium, but that doesn't actually show up in the natural environment, right? So whatever event happened about 4.5 billion years ago, probably some supernova that created all the element or almost all the elements that we have on Earth from like basically hydrogen, right? So we get all these elements, but they only go up to uranium. Again, plutonium you can create artificially, right? But uranium is radioactive, and so are all these elements. They all have some half-life. There's some rate of decay, right? Until it reaches lead, and down here Pb is lead, and that one's stable. And so if you pick up a rock, you say like, what's the ratio of lead to uranium in that rock, right? And you know how much time it takes for like what's the half-life at each stage of the process. So you can put that together and figure out what is the age of the rock. Yeah. So 4.5 billion years old, all the rocks we found. All right, extra little detail here. Here's the chief scientist who found that process, this lead uranium dating, right? And there's an extra part of the story, which is you guys know if you go fill up gasoline at a gas station and you get unleaded gasoline, well, that used to not be the case. There used to be lead in gasoline. Actually, it was specifically, where is it? Tetraethyl lead, right? So part of his process, he had to very carefully figure out how much lead was in rocks, but it's a very subtle amount. And he realized that there's lead all over the environment. And just trying, okay, so why is that? Oh, okay, because everybody's pumping this leaded gasoline into the environment and getting the atmosphere. There's a case to be made that aggregate IQ points actually went down during the 20th century while lead was being spewed all in the environment, and that crime possibly went up also because of that. Right? But since we took lead out, then we're a little bit better off, right? So yeah, we used to have lead in like canning and like food cans and stuff, right? So yeah, so this guy's research and trying to figure out how old is the Earth, yeah, eventually led to us getting unleaded gasoline. Yay! So we're healthier for that, right? There's also here. I want to show you guys. Let's do carbon-14 dating. All right, so there you go. This is if you guys ever hear carbon dating or want to get into archaeology and like how old is this artifact? As long as it's organic, it's made out of living material at some point, you can use this method. Right? So radioactive decay, carbon-14 dating is a specific example of this radioactive decay. Oh, here, let me show you guys the poster I got for this. Right, we're gonna pretty much copy this poster into this quadrant. Right, so there you go. There's a nice looking poster on this, right? Right. So here, I'll reconstruct that graph and show you guys along the way what I'm doing. So let's say you're looking at the amount of some substance, in this case, carbon-14, say as a function of time, right? Or in biological material, right? Let's say you like dig up an old skeleton or like some old paper that was made out of plant material, right? Maybe some concentration of this carbon-14. And this is a really rare isotope of carbon. They say what, like 12 atoms out of a trillion or something like that, right? But it's pretty well consistent for anything that's alive and breathing, right? But it starts to dissipate as soon as you die. And this has a half-life of, here, I'll write this down here, carbon-14 half-life, T sub 1 half half-life is 5,730 years. Okay. What does that mean? Well, let's look on the graph. Let's say at time 0, like right now, sitting in this room, all of us have some concentration of carbon-14 in us. Not very much, but I'll list that right here as like an intercept point, right? Right now, some point we're going to die, and then say you wait 5,700 years, and somebody's digging up our skeletons, like, hey, look, it's them. And 5,700 years. Here's 1 half-life has passed that point. Right? And they went, hey, how old is the skeleton? Right. Well, what they'll find is that there's half the concentration of carbon-14 that there would have been for a living person. Oh, that's how you know it's 5,700 years old. Right. Suppose you dig up a skeleton and run the analysis, and there's a quarter of the original amount. Oh, well, that means that 2 half-lives have passed, 2 T1 half. So it's about 11,000 years old. Right. Suppose you get 1/8 of the original amount. Okay, that means 3 half-lives have passed, right? So half, a quarter, an eighth, 1/16. Right? Okay, so you could keep going on. There's 3 half-lives that passed, right? You guys get the idea, right? It's going to create this curve. Right? It's an exponential curve, right, with a negative exponent. I give you guys a couple of equations. There's 2 main ways to describe the equation. Let's start with the more intuitive one. The amount that you have is equal to the initial amount times, okay? So we're going to start with some initial, maybe concentration, right? And then you dig up some artifact and you get some measured amount, right? So what's the connection with time, right? Well, it depends how many half-lives have passed. So I'm going to say times 1/2 to the power of, and then the time that's actually passed divided by the half-life, right? So that exponent I just wrote is effectively a count of the number of half-lives that have passed, right? So for example, if 5,700 years have passed and 5,700 years is the half-life of carbon-14, 5,700 is 1. 1/2 to the power 1, that means you multiply by half 1 time. Oh, so you have half the amount that you started with. If you plug in 11,000 years, 11,000 on 5,700 is pretty close to 2 half-lives have passed. 1/2 squared. Okay, so multiplying a half twice. So now we're going to end up with a quarter of what we originally started with, right? Now, that's the more intuitive way. There's a more maybe mathematical proper way to do it. Do you guys learn about natural logarithms, like base E, right? E 2.71828, irrational number, right? So let's do an equation here. Yeah, this is, so we'll take say the amount we ended up with is the initial amount we start with, right, times, right, here's a little bit different. I'm going to use that number E. Yeah, it's like 2.71828 to the negative KT, right? So T is still the amount of time that's passed, right? That K corresponds to some particular half-life. I'll give you guys that too. So the K value in that exponent, which is for carbon-14, is, where we got here, 1.21 times 10 to the negative 4. And that's 1/years is the unit on that, right? Right, so hey, we're still here for a while. Still got some time, right? Right, so you guys got that? All right. What? All right, so you guys good with carbon dating and radioactive? Okay. All right. These last couple here, I'll just do with you guys here. So what is unification, string theory, M theory? So really there's 2 different sets of laws of physics that we got in this class. Like most of this class up until a couple weeks ago was just classical macroscopic physics, right? And for the last week or so, you guys have been looking at these really weird cases of physics down at the atomic level, which follows its own probabilistic type rules, right? Well, what if you have some scenario where those 2 sets of laws of physics clash? Like say like near a black hole or inside a black hole, or say beginning of the universe, Big Bang, where you have like large masses but also small sizes, right? Well, what set of laws of physics do you use, or what exactly is going on? So that's where unification comes in. This is an attempt to unify general relativity think classic macroscopic physics, right? Like Newtonian gravitation is really a simplification of general relativity, right? So Einstein relativity. So this is macroscopic. Okay, so your classic laws of physics, right? We're going to unify that and quantum mechanics. Right, which is say like atomic physics. All right. All right. Can we unify this all into one theory of everything? And no one's ever been able to do this so far, right? Can you combine say gravitation with the standard model, right? Is another way to phrase this, right? Okay. Okay. Now, if you could have say like one unified theory of everything that could explain everything, then you'd have consistent laws that where you could actually investigate questions like what's going on, say like inside a black hole or near the Big Bang, and have some insight into that. Right. And then the engineering side of this, here's number 28, nanotechnology. Can you do? I'm just going to write this very simply: engineering at the atomic scale. Right. It's entirely likely. Suppose you run forward the clock like 1,000 years from now, right? Technology is probably going to be so crazy that say like, oh, I'm hungry. I want a carrot, and then you snap your fingers, and you got your machine, and you pour some dirt into it, and it rearranges the molecules and spits you out a carrot, right? Right, so something like that. That would probably take a lot of energy, right? But could it in principle be done? Yeah, I mean, so or maybe probably technology is a little bit closer. Is could you have like little nanobots that to like go through your bloodstream and clear out your arteries and remove cancer cells and that kind of thing, right? That's probably, yeah, I don't know, maybe in the next 100 years, we may have something like that, right? But you have to be working with these little nanobots that are going to be so small that you have to maybe consider quantum mechanics too, right? So there you go. All right, so you guys good with those? All right, so yeah, that is going to be a wrap on this quantum journal. So that is the end of this project. If you have all 28 quadrants filled and you want to turn that to the grade tray, then I will score that, give you guys points for that. If you were absent or you're missing any of these for any reason and you need some extra time, then that's right too. You don't have to turn it in today, but turn it in pretty soon at some point. Tomorrow, I will get you guys a final exam review and we'll start the final exam review tomorrow.